Okay, again, no? So this is the summary of what we will be taking up in today's lecture. So let's first discuss equivalence. Two electric circuits are said to be equivalent with respect to a pair of terminals if at these terminals identical currents flow when identical voltages are applied. So what does this mean? Let's say I have two circuits, circuit 1 and circuit 2. I can access circuit 1 through terminals A and B, and I can access circuit 2 through terminals X and Y. So let's say I apply a voltage V1 to circuit 1 and I apply a voltage V2 to circuit 2. If I set V1 equal to V2, and it turns out that I1 will be equal to I2, then with respect to terminals A, B, and XY, circuit 1 and circuit 2 are equivalent. So what exactly is the repercussion of that? No? That means that if I have a third circuit, let's say I have a third circuit, so let me draw that here. Okay, so this is circuit 3 actually. Okay, this can be circuit 1 or circuit 2. Circuit 3 will not be able to tell the difference. So circuit 3 cannot tell the difference. So hindi malalaman ng circuit 3 kung ano yung nakakabit sa kanya. Circuit 1 ba yung nakakabit sa kanya or circuit 2 ba yung nakakabit sa kanya? No? This is with respect to terminals A and B or X and Y. So that is the principle of equivalence. So this is what we're going to use in circuit simplification. No? So this is performed when we're interested in just a few unknowns in a circuit. The technique is to transform a portion of the circuit into a simpler equivalent circuit while preserving the unknown quantities to be determined. This is very important. You have to preserve the unknown quantities to be determined. Later on, I'm going to explain further what I mean by that. Now, the simpler circuit makes it easier to compute for the desired quantities. So let's take the first technique for circuit simplification, and this is resistances in series. So I have here N resistors in series. Later on, I'll explain what series means. And I am saying that with respect to terminals A and B, I can replace this with a single equivalent resistance, and a circuit will now not know the difference whether it is the left circuit or the right circuit that is connected to it. It turns out the equivalent resistance is equal to the sum of the individual resistances. And it's very easy to show that. Okay. Let's say I apply a voltage here. Okay. That voltage is going to cause a current to flow. If the two are equivalent, applying the same voltage here will cause the same current to flow. Now, from Kirchhoff's voltage law, okay, if this is my current I flowing in this circuit, then I know that I will have in the individual voltages across my resistances. I'm going to have here VR1, VR2. Take note of the polarity. No? The polarity is always in the direction of current. No? So from plus to minus in the direction of current. So all the way to VRs of N. And because of KVL, so this is the left circuit. Using KVL, or Kirchhoff's voltage law, you have V is equal to VR1 plus VR2 all the way to VRN. But using Ohm's law, we know that VR1 is equal to I times R1. No? VR2 is equal to I times R2 and so forth. No? VRN is equal to I times Rn. So I can simply write the KVL equation as V is equal to I times R1 plus R2 plus R3 all the way to plus Rs of n. If I take a look at the right circuit, using Ohm's law, simple Ohm's law, I know that V is equal to IR. So if this V is equal to this V, and this I is equal to this I, then that means this expression must be equal to this. Those must be equal. And that is what we're saying here. R equivalent is equal to R1 plus R2 plus R3 all the way to plus Rn. So it's very simple. No? Now, when are two elements in series? I told you I will explain when two elements are in series. Two elements are in series if they are interconnected at only one point and if nothing else is connected at that point. So we are in series if interconnected at one point with nothing else connected at that point. Some other way of describing a series connection is when the head of one element is connected to the tail of another element with nothing else connected at this point of interconnection. Okay, in the previous slide, I said that you transform a portion of the circuit into a simpler equivalent circuit while preserving the unknown quantities to be determined. So why must you preserve the unknown quantity? So for example, no, what if my unknown quantity were VR2? So I want to determine VR2. That is my unknown. Okay. The minute I combine all of these resistors into one equivalent resistance, nawawala na yung R2 ko. My R2 will cease to exist. And therefore, how can I define VR2? So I will not be able to combine R2 with the other resistances if my unknown is VR2. Otherwise, I am not preserving the unknown quantity that I want to determine. So that's very important in circuit simplification. Are there any questions? Any questions? Okay. Let's go to resistances in parallel. Okay. Two elements are in parallel if they are interconnected at both their ends. At both their ends. No? So if you take a look at R1 and R1 and R2 are parallel because at this end, they are interconnected, and at this end, they are also interconnected. They have to be interconnected at both their ends. For example, no? And this is a common mistake. Let's say this is R1. This is R2. If I have another element here, okay, if I have another element there, let's say this is R3, R1 is no longer in parallel with R2. And like I said, that's a common mistake of students. They have to be interconnected at both their ends. Okay, it's very easy to show that this equivalent resistance between A and B follows this relationship. 1 over Req is equal to 1 over R1 plus 1 over R2 plus 1 over R3 plus 1 over Rn. By the way, what is 1 over R? Anyone? Can you remind me? Can someone shout it out? Ano yung 1 over R?
G po.
G, right? No? G is conductance. So in effect, this equation can be written as G equivalent is equal to G1 plus G2 all the way to plus G of n. No? So this is the sum of conductances. Okay, sum of conductances. And it's very easy to show that the left circuit and the right circuit are equivalent. We can do the same. We can do the same thing. No? If I apply a voltage V here, expect the current I to flow this way. The same voltage V here should cause the same current I to flow. Now, what is I in this particular case? No? Here on the left. No? Using Kirchhoff's current law, okay, this is my node. What is my node? This is my node. No? This whole thing is my node. Okay, so you're using Kirchhoff's current law. I, okay, this current is equal to I1 plus I2 plus I3 all the way to plus IRN. So for the left side, I is equal to I1 plus I2 all the way to plus I R's of n. Okay, but I1 is just V over R1. The current I1 is the voltage across this resistor divided by its resistance value. But what is the voltage across this resistor? You will notice that this voltage V is applied across all resistors in parallel. So I1 is V over R1, I2 is V over R2, and so forth, no? Sorry. And so forth. So what is this? This is just I is equal to V over R1 plus V over R2 plus V over R's of n, or V times 1 over R1 plus 1 over R2 all the way to 1 over R's of n. Okay. On the other hand, if I look at the right side, I look at this side, from Ohm's law, what is I? Okay, I is equal to V multiplied by 1 over R equivalent. So if this I is equal to this I, and this V is equal to this V, okay, then this must be equal to this, which is what we're saying here. Okay, you have a special case when you have two resistors in parallel, the equivalent resistance, you just remember, no? Product over sum. So this is product over sum. The equivalent resistance is the product of the two resistors divided by the sum of the two resistors. And note that when you have two resistors in parallel, the equivalent resistance will always be smaller than either resistor. Yung REQ will be smaller than R1 and smaller than R2. If R1 and R2 are not equal to 0, no? REQ will be smaller than either resistor. Okay. What if I have two equal resistors in parallel? What is the equivalent resistance? Anyone? What will happen if R1 and R2 are equal? What is the equivalent resistance? Can I hear a shout out of the answer? Anyone? Or should I call someone to answer?
Ako po, sir. Divide lang po sa 2. Kasi
Okay,
R
that's right,
squared.
no? Yeah, that's right, no? If you have two equal resistors in parallel, then the equivalent resistance is just the resistor divided by 2. If you have three equal resistors in parallel, the equivalent resistance will be the resistance divided by 3, no? And so forth. Okay. What will happen if I have a resistor and I short it? No? What is the equivalent resistance? What is REQ? Anyone? If I connect a short across a resistor, what is the equivalent resistance? Sige, magtatawag na ako ng tao, no? Who is Albert? Albert Castillo?
Yes, pa.
Yeah. What will happen? Ano yung equivalent resistance in this case? Ayaw mong humula?
Yun din pong resistance ng resistor.
Ito R.
Apa.
Good guess, no? Good try, no? A short circuit is a resistance whose value is what? Anyone? Other than Albert?
Zero po.
That's right, no? A short circuit is a resistance whose value is 0. So what will happen to this expression if one of the resistors is 0? Your equivalent resistance will just be equal to 0, right? So in this particular case, REQ will be equal to 0. Okay. Anyway, that's resistance in parallel, no? So I already explained when two elements are in parallel. Again, you must preserve the quantity that you want to determine. So just as in the case with resistances in series, let's say my unknown is I2, I want to determine I2, then I should not combine R2 with other resistances. Otherwise, mawawala yung R2 and therefore mawawala din yung I2. You have to preserve the quantity that you want to determine. Okay, here's an example. Determine the voltage V by simplifying the circuit seen by the current source at terminals A and B. So this is a classic circuit simplification problem. I have a current source, and my only unknown, the only thing that I have to determine is this voltage. Right? So I want to simplify the problem. The way I simplify the problem, itong circuit na to, I will replace by just a single equivalent resistance. And by doing that, my solution to the problem will just reduce to Ohm's law. I can get V by multiplying my current source with my equivalent resistance. So with respect to terminals AB, I want to reduce this. Okay, I start farthest from AB and work my way toward AB. That's how I have to do it. So remember, I have to preserve terminals A and B. So I will start farthest from AB and work toward AB. So what do you first see? Ano yung una mo nakikita? Ang una mo makikita is these two are in series. So these two are in series. So I can combine these two. Okay. I can combine these two. So this is just going to be the sum. No? The sum. This is just going to be 16 ohms. Okay. So what next do you see? Anyone? Just shout it out. Anong next na nakikita nyo?
Parallel po siya sa 64.
Yeah, 16 is parallel to 64. No? So with respect now to these terminals here, let's say with respect to these terminals, I wanted to replace this with a single resistor. This is going to be 16 ohms in parallel with 64 ohms. I need my calculator. I didn't solve this ahead. Okay, which is 12.8 ohms. So this is 12.8 ohms. So dito, with respect to these two terminals, no? With respect to these two terminals, this is equivalent to 12.8 ohms. And then what do I see next? I see that this and this are in series. Okay, so with respect now to these two terminals, dito naman, no? I have 12.8 plus 7.2. So this will give me 20 ohms. Okay. Finally, what is my single equivalent resistance? With respect to AB. So anong final equivalent resistance ko? Anyone?
12 po.
12, that's right, no? 12 ohms, which is a product. So 20 times 30, 600 divided by sum, which is 50, no? So that is 12 ohms. Okay. So see now how simple the problem has become, no? Because now V is just simply equal to 5 amperes times 12 ohms, which is 60 volts. Okay. Very easy. So that's circuit simplification, simplification of resistive networks. Okay, here's an example. Determine the equivalent resistance of the circuit with respect to terminals A and B. So this is how we might complicate the appearance of a network. Okay. Does anyone see any elements in series or parallel? Can anyone identify any elements in series or parallel? Anyone? Does it look intimidating? Medyo nakakatakot yung itsura, di ba? Okay, here's how I would do this. No, of course, okay, something about wires, no? Wires. Wires can be stretched or compressed without affecting circuit behavior. Okay, that's the thing about wires. If it is an ideal wire, a wire is a conductor with zero resistance. That is an ideal wire. No? An ideal wire has zero resistance. That wire can be stretched or can be compressed even to a single point without affecting circuit behavior. That's the reason why earlier, dun sa resistors in parallel, we said that that entire top wire was just a node because you can compress it to a single point. Okay. If that's the case, ano ibig sabihin nun, ano? That means, okay, this is point B. This is point B. If I take a look at this wire, this is also point B. Ito, this is also point B. Okay. This is point A. Okay. With respect to this wire, this is also point A. No? So ang sinasabi ko, this point is the same as this point. No? That's the same node. That's basically the same node. And this point is also the same as this point. Okay, then I have a third point here, a third point of interconnection of elements, and that is this. No? So those are my 3 points of interest. Okay, now what can I do so that I can understand the circuit better? I can redraw it. No? So let me redraw the circuit. Okay, so let me call this, let me call this point A. So that's actually a wire, which is a single node. Let me call this B. So this is A, this is B. And then let's say I have C here. No? The reason why I make it smaller, you'll see in a while. Okay, this resistor is connected between A and B. That's 4K. That's connected between A and B. So let me cross that out, and I show that as being connected between A and B. Okay, that's 4K. What about this? Where is this connected? Also between A and B. Right? This 4K is also connected between A and B. So I have another 4K here. Okay, so I consider that already. If I take a look at this 4K, it is also connected between A and B. And this 4K is also connected between A and B. So meron pa akong dalawang resistor connected between A and B. I have 2 more resistors connected between A and B. Another 4K here. Another 4K here. Okay, this is C. Okay. So, in effect, this is parallel to this, is parallel to this, is also parallel to this. Okay, now, what about this resistor? This resistor is between A and C. No? So itong 1K na to is between A and C. 1K. This resistor is between B and C. That's between B and C. This resistor is between B and C. And this resistor is between A and C. So I have another one between B and C. And I have another one between A and C. Okay. Now, do you see which are in series and which are in parallel? Okay, having said that, please compute what the resistance is between A and B. So I want the resistance between A and B. Okay, so can someone compute that for me, please? I want to hear the answer from you. Pwede niyong i-chat sa akin, no? Let's see who can. I don't want this to be a contest, no, but let's see who can get it first anyway. No? Okay, I have one answer already. Okay, another answer. Okay. Tama, no? Let's take a look, no? Okay, these two are in parallel. Okay. These two are in parallel, so the parallel equivalent of these two, remember, two equal resistances in parallel is 1/2, no? 1/2 of one resistor. So the equivalent resistance of these two is 500. Okay. These are also in parallel. Equivalent resistance is also 500. And this 500 is in series with this 500. So itong apat na resistor na to is one resistance between A and B that is equal to 1,000. And then here I have 4 resistors, all 4K. So you have 4 resistors, all 4K. The parallel combination will be 1/4 of 4K. So also 1K. No? So I have 1K in parallel with 1K, and the answer is 500 ohms. No? So R equivalent or RAB is 500 ohms. Okay. So if you look at this, medyo nakakalitong tignan, but all you have to do is really figure out what is connected between what. It helps to redraw. You can redraw it this way, no? So that kitang-kita nyo which are in series and which are in parallel. Are there any questions? Any questions? Okay, here's another example. Determine the current supplied by the 4.8 voltage source. Can someone tell me or show me any two resistors in series? Someone, anyone? Excuse me, no? Can anyone tell me if there are any two resistors in series? Meron ba? Sino bang tatanong ko? Ryan, Tanko? Can you tell me two resistors that are in series? Ryan?
Oh, yes. Is it the 30 ohm and the 15 ohm? Sure.
30 ohm and 15 ohm, no? So let me test that, no? Okay, they're interconnected at one point, but there's another element that is also connected there, no? So by definition, when at the point of interconnection of the two elements, there's another element connected, that is no longer in series. No? Anyway, good try, no? So anyway, to get down to it, there are no two elements here that are, excuse me. Excuse me, no? There are no two elements here that are in series. No. There are no two elements that are in series. So like I said, you cannot consider 30 and 15 to be in series because there's something else connected at their point of interconnection. Are there any two elements here that are in parallel? You're also going to find out that there are none. no? Because for two elements to be in parallel, they must be interconnected at both their ends. And there are no two elements here that are interconnected at both their ends. Okay. For example, this is connected here at this end, but this is not connected to this. No, there's an element in between. So there are no two elements that are in series, or there are no two elements that are in parallel. So does that mean that I cannot simplify this? Because remember, the only thing I'm looking for here is the current supplied by the 4.8 volt voltage source. No, so this is my only unknown. So it would be nice if I could simplify this, okay, to make it easy for me to compute for I. Okay, fortunately, this can be simplified. And the way to simplify that is using either a delta to y or a y to delta transformation. Okay. Delta to y or y to delta transformation. Now, when we talk about delta to y or y to delta, we're talking about equivalence with respect to 3 points. No? So earlier, we were talking about equivalence with respect to 2 points. Now, this is equivalence with respect to 3 points. In this particular case, A, B, C, and D. No? So if I have resistors arranged this way, I can convert it to resistors arranged this way. And this is my conversion formula. No? So we call this delta to y, no? For obvious reasons. I have a common denominator. My denominator is the sum of the 3 resistances. And my numerator, okay, let's take a look. No? If I'm computing for RA, my numerator is this resistance and this resistance. No? It is the resistance that is in the sides of RA in the original delta. So ito yung RA, this is RA. Okay. My numerator is going to be the resistor connected here. Sorry, and the resistor connected here. So that is R1 and R3. So that is RA. RA is R1, R3 divided by my denominator, which is the sum of all resistances. So same thing with RB. No? RB. The resistor connected to B in the delta is R1 and R2. Okay, so R1, R2 over my denominator. And then C, the resistors connected to C in the delta is R3 and R2. So R2, R3 divided by my denominator. So that's converting from the delta to the Y. When I convert now from the Y to the delta, so this is the other way around, I have a common numerator. And my numerator is the product, the sum of the products of the resistances taken 2 at a time. The sum of the products of the resistances taken 2 at a time. So that's RA, RB plus RB, RC plus RC, RA. Okay. Now, what is my numerator? No? If I'm computing for R1, okay, my numerator is the resistance connected opposite R1 in the Y. No? So R1 is here, R1 is here. My numerator is this resistance. It is opposite R1 in the Y. Okay. So that's RC. No? Sorry, my denominator, not my numerator. My numerator is the sum of the products. So my denominator. So R1 is N over RC. No? R2 is N over RA. No? So this is R2 in the Y. Opposite that is RA. And R3 is N over R sub B. So going back to this example, okay, do I see any delta or do I see any Y? Okay. Anyone? How many deltas are there? How many deltas are there? Can you tell me?
Dalawa po.
Yeah, there are two deltas, ano? These three resistors, 30, 10, and 40, that forms a delta. These three resistors, the 10, 15, and the 20, that also forms a delta. No, I can redraw this to be a triangle. No? I can also redraw this to be a triangle at the top. No? So there are two deltas. So I can convert either of those deltas to y. No? And there are also two y's. No? So these three resistors forms a y, 30, 10, and 15. Note that these three resistors, 40, 10, and 20, also forms a y. Itong tatlong resistor na to. Okay. So there are two deltas and two y's. So what did I choose to do? I chose to convert this to a delta. So if I convert this to a delta, I will have one resistor here. I'll have one resistor here, another resistor here, and another resistor here. Then I can get rid of the y in the middle. So that's what I did. That's what I did here. So using the formulas that I previously gave, using these formulas, okay, let's see, what is this? No, this resistance, okay, is equal to, okay, this is y to delta, no, y to delta. So I have my numerator, no, RA/RB plus RC plus RC/RA, okay, divided by, okay, this resistance. I have to divide it by this. Okay, so ano yun, no? 30 times 10 plus 10, basically, no, yung itong resistor na to, this is 30 times 10 plus 10 times 15 plus 15 times 30 divided by 15. That's that resistance. Okay, and if you compute that, you're going to come up with 60. Okay, this will be 90, and this is going to be 30. So now you can see elements that are in parallel. These two are now in parallel. These two are now in parallel. The parallel combination of this is now in series with this, the parallel combination of this. And then now this whole thing is now in parallel with your 90. Okay, so just do the math. The equivalent resistance is going to be 25.71 ohms. And 48 volts 4.8 volts divided by 25.71, you're just going to get 0.187 amperes. Are there any questions? Any questions? Okay. So that's circuit simplification when you have resistive networks. Let's continue. What happens when you have voltage sources in series? Voltage sources in series. If I have this particular arrangement, no, V1 in series with V2 in series with V3 all the way to Vn, if I apply Kirchhoff's voltage law to terminals A and B, okay, I'm going to get VAB, which is equal to V equivalent, is just V1 plus V2 plus V3 all the way to plus Vn. So I can replace this all with a single voltage source, which is the algebraic sum of the various voltage sources. Now note, you have to take note of the polarity. For example, no, what if this is A and B, and I have here V1, and then I have minus plus V2. What is VAB? No, VAB will be V1 minus V2 because of the polarity. Okay, that will be my V equivalent. No? That is my V equivalent. No? That is the voltage source that a single voltage source across AB that the sources in series will look like. What about current sources in series? Okay. If I apply KCL to any point of interconnection between two sources, for example, if I apply KCL here, no? Kirchhoff's current law here, I'm going to get here I1 is equal to I2. If I apply Kirchhoff's current law here, I'm going to get I2 is equal to I3. In other words, for this circuit to be valid, okay, I1 must be equal to I2, must be equal to I3, must be equal to ISO of n. No? And I can represent all of these current sources as a single source that is just equal to I1, which is equal to I2, which is equal to I3, and so forth. But all of this would have to be equal to each other for the circuit to be valid. So last time we took up valid and invalid circuits. When is a circuit not valid? The circuit is not valid if it does not follow either Kirchhoff's voltage law or Kirchhoff's current law. If it violates either of those two, then it is an invalid circuit. So those are sources in series. Again, you have to be careful of, well, in this case, no, all of the currents have to be in the same direction. If one of these currents is in the opposite direction, then you already know that that's an invalid circuit. What about sources in parallel? So here I have voltage sources in parallel. So I can represent all of these voltage sources as a single source, provided all of these sources are equal. Why? No? If I apply KVL to any of these loops, let's say I apply KVL here, okay, I'm going to get V1 is equal to V2. If I apply KVL here, I'm going to get V2 is equal to V3. Therefore, V1 must equal to V2 must equal to V3 all the way to V sub n. And I can represent all of this with just a single voltage source between A and B equal to V1. Now, when I have current sources in parallel, then it's a different story. My equivalent current will be the algebraic sum of the various currents, where I have to take note of the current direction. So now you can simplify voltages in parallel, voltages in series, currents in parallel, and currents in series. Any question? Okay, here's a very trivial example. For the circuit shown, what value of alpha is required for the circuit to be valid? Okay. First of all, we identified what this was last meeting. What do you call this? What type of source is this? Anyone? Can someone just shout it out to me?
Dependent source po.
Yeah. What type of dependent source in particular? Anong klaseng dependent source?
Voltage controlled current source po.
Voltage controlled current source. That's right. No, it's a voltage controlled current source. Okay. So what value of alpha is required for the circuit to be valid? let me apply KCL here. No? KCL at A. Okay, I'm going to get, okay, KCL, the sum of the currents leaving the particular node is equal to 0. So I'm going to get 15 plus alpha v of x is equal to 0, or, okay, alpha v of x is equal to minus 15. No? So that's applying KCL at this point. No? Now, what is v of x? V of x, if you take a look here, anong value ng v of x? Anyone? Anong value ng v of x?
Negative 25 po.
That's right, no? This is minus 25 volts. Okay. So right away, I can compute for alpha. No? Alpha is equal to minus 15 over minus 25. So what is this? This is 0.6. Anong units? Don't forget the units. Anong units ang alpha? Units of alpha? Anyone?
Siemens po ba?
Correct. No, very good. Siemens. Okay. So the units is in Siemens. Okay. So letter B. No? For the calculated value of alpha, find the power associated with the 25-volt source. Actually, you don't even have to know alpha to find the power associated with the 25-volt source. Ano yung power associated with the 25-volt source? So this is letter A, no? Letter B. What is the power associated with the 25-volt source? It's very easy to see that. Let me draw my source. Okay, this is 25 volts. And because of my current source, I have a current that is 15 amperes that is flowing this way. Okay. So my first question is, does this follow the passive sign convention? Yes or no? Does that follow the passive sign convention? Anyone?
No po.
No? Nice try. If it's not no, then it's probably yes, ano? Yes, no? Naalala niyo yung passive sign convention? The passive sign convention means that the reference direction of current is in the direction of voltage drop. No? Note that my current is flowing from plus to minus. No? It is in the direction of voltage drop. Right? So this actually follows the passive sign convention. No? So this is consistent with the passive sign convention. And therefore, my power will be positive. No? My power is just 15 times 25. 15 times 25. Okay? Ano 15 times 25? Hindi na ako mag-multiply. 375 watts. Okay. So what is the answer to letter C? No? Well, andito na, no? Answer to letter C is it is absorbing. Kasi nga, if it follows the passive sign convention, then that means that power is being delivered to the element, or the element is absorbing power. So in this particular case, itong 25-volt source is really not delivering power. It is absorbing power. Absorbing power from the 15-ampere source. So imbis na siya yung nagbibigay ng power, siya yung tumatanggap ng power. Okay? So that's That's the answer to this example. Okay, we have two more topics to discuss: voltage division and current division. No? Let me speed up a little bit. No? Voltage division, the total voltage across a group of resistors in series distributes across the individual resistors proportional to resistor value. Proportional to resistor value. No? Intuitively, it makes sense. No, intuitively. What if I have a voltage here? Okay, let's call this V, and these are equal. No? Are equal. So let's say this is V1 and this is V2. Okay, so if these two resistors are equal, what is the relationship between V1 and V2? What will they be? They will also be equal, right? They will also be equal. In other words, itong voltage na to, maghahati lang dito sa dalawang to. No? Because R is equal, this voltage will split itself equally between the top resistor and the bottom resistor. No? The voltage will distribute according to the resistance value. So if I have three resistors that are equal, the voltage will just be split 1/3, 1/3, 1/3. Okay. What if this is R and this is 2R? Okay, what will be the split? Ibig sabihin, V2, okay, V2 will be 2 times V1. Right? Because this has twice the resistor, it will also have twice the voltage. So ang magiging split niyan, ito magiging 1/3, ito magiging 2/3. Right? Of the total, 1/3 will go here, 2/3 will go here, so that V2 will be twice V1. It will split proportional to the resistance value. And if you try to express that mathematically, this is your mathematical expression. V sub I is equal to V, itong total V across all the resistors, multiplied by Ri, divided by the sum of all the resistances. Okay. So here's a simple example. A photocell is a variable resistor whose resistance is inversely proportional to incident light. The circuit shown was found to have the following values of V out under different lighting conditions. So this is a photocell. Okay. There's light. Then the value of the resistor is a function of light. No? And if this is a semiconductor photocell, the resistance value decreases as your light intensity increases. So when it is bright, you have a small resistance. When it is dark, you have a large resistance. By voltage divider, we say that V out is equal to 5 volts multiplied by R. R is the resistance of your photocell divided by R plus 5.6K. This is by voltage divider. Remember that this 5 volts, when you see this symbol, this means that there's 5 volts here with respect to your reference. There's 5 volts here with respect to your reference. Or another way of showing this is parang meron kang supply dito na 5 volts, no? This way, connected that way. So by voltage divider, this voltage or the voltage across this and the voltage across this will distribute proportional to the resistor value. No? And this is going to be your formula for V out. Okay. If you solve for R here, solving for R, I'm going to get R is equal to V out multiplied by 5.6K divided by 5 volts minus V out. Okay. So if I apply this formula to these different values of V out, I'm just going to get these values. So this is going to be 1004 ohms. This is going to be 7013 ohms. And this is going to be 10,042 ohms. So it's pretty straightforward. Current division is the dual of voltage division. Sa voltage division, your your voltages distribute proportional to the resistance values. In current division, your currents distribute to the different resistors in parallel this time according to conductance value. So it's according to conductance value. Okay. So for example, if I have just two resistors and they are equal, then the currents that will flow would be equal. No? If one resistor has a conductance that is twice a second resistor, then the current that will flow will be in that resistor will be twice that of the second resistor. Anyway, this is your formula. No? So this is expressed in terms of conductance. Of course, you can get an equivalent expression in terms of resistance. You have a special case when you have two resistors in parallel. So that's two resistors in parallel. That's this. Okay, R1, R2. Okay, what is I1? This is I1. I1 is equal to I multiplied by R2. So note R2, no? R2 is the other resistor divided by the sum. And then yung I2 naman, I2 is equal to I multiplied by R1. So this is I2, but this is R1 divided by the sum. No? And you can work that out from this expression. Okay. Let me ask you a question. So let's say I have a short circuit here. This is R1, and this is I. What is the value of I1? What is the value of I1? Anyone? Anyone?
0 po, sir.
Right. Bakit 0? Correct. No? 0. Bakit 0? Was that just a guess or intuition? No? But you're correct. It's 0. No? I1 will be equal to 0. Bakit, no? Because this is, let's say this is R2. This R2 is equal to 0. Right? So if you use this formula, okay, I1, itong R2 natin is equal to 0. And therefore, I1 will be equal to 0. Or another way, what is the voltage across a short circuit? Voltage across your short circuit is 0. And therefore, using Ohm's law, 0 over R1 will be equal to 0. Okay. So what is this telling us? No? When you have a short circuit across any element, that short circuit will attract all the current. Wala nang dadaan na current dun sa element na yon. Because all of this I now lahat nitong I dito nadadaan, no? This is going to be equal to I. No? All this current here is going to flow here. Walang dadaan dito sa gitna. No? That's why we have this expression, current will always look for the path of least resistance. And when that resistance is 0, all the current will go to that path. No? Current looks for the path of least resistance. When that resistance is 0, all the current will go through that path. No? This is just an I'll tell you a story. No? It'll only take a few minutes. No? I'll tell you a story. I have a friend, a good friend, in fact, that survived getting struck by lightning. And the reason why he survived getting struck by lightning was, okay, he was holding out an umbrella, and on his other hand, he was holding a golf club that was connected to ground. And when the lightning hit his umbrella, okay, because of his golf club that was connected, that he was leaning on, connected to ground, the current passed through the umbrella, and then through he was wet, through his surface, no, to the golf club to ground. It was drawn away by that path of low resistance. So walang masyadong current na nagdaan sa katawan niya. No? Halos dumaan lang dun sa path ng low resistance. If he wasn't holding his golf club connected to the ground, he would have died. But that saved him. That golf club connected to the ground saved him, because the current looked for the path of lower resistance. Anyway, that's just a story. Okay, the rest of my slides are really just examples. Okay, maybe let's do this one. Let's do this one. And then the second one is actually a problem that for those of you that attended my supplementary lecture last week, that I already discussed, but it can also be solved using voltage division and current division. So let's just do this example very quickly. Okay, an ammeter is an instrument that measures the current flowing through it. No, so this is my ammeter. Okay, this is my ammeter. Ito lang yung ammeter ko, no? This is my ammeter. And the ammeter measures the current that flows through it, no? So if this is I, pag tinignan mo yung face ng ammeter, let's say it is an analog ammeter, pag tinignan mo yung face niya, you have a needle, and then you have a scale, no? So maybe this is 1, and this will be, let's say 1 MA, no? Something like that. So this is the face of your ammeter. So depending on the current here, depending on the current that will flow, okay, this needle is going to deflect to the value of current that you can read in the scale. Okay, so that's an ammeter. An ammeter is a device that measures the current that flows through it. The equivalent circuit of this particular ammeter is 50 ohms. So you might think of this as a resistance equal to 50 ohms. To increase the maximum current that A can indicate, so this is my original ammeter, okay, I connect a resistor in parallel with it. And in this particular case, I want this resistor to draw 90% of this current. No? In other words, this is 0.9I, and this will just be 0.1I. No? If this is the current that is flowing, the total current that is flowing, I want 90% to pass here, and I only want 10% to pass through this ammeter. So the first question is, what should be the value of RSH? No? The answer is 5.56 ohms. Now, how did I get that? Okay, and I can solve for that using current division. No? So okay, ito na lang, no? 0.9I, 0.9I is equal to I, this current, the total current, multiplied by 50 over 50 plus RSH. That's current division. No? So this current is equal to this current multiplied by 50 divided by 50 plus RSH. And if I solve that, I'm going to get RSH is equal to 5.56 ohms. Okay, now what is the current now that I can measure using this system? No? So that's letter B. So now, supposing this is the current I want to measure, if this is the current that I want to measure, itong scale na to, I can redraw this, no? Originally, without this resistor, I could measure 0 to 1 mA. But now, okay, because of this resistor, okay, I can get as much as 10 mA flowing. Okay, 9 mA will go through RSH and only 1 mA will go to my 50 ohms. Right? So I can redraw this, no? Instead of showing 0 to 1 mA, I can now show this as 0 to 10 mA because 90% of the current is being drawn by RSH, no? Only 10% is flowing here. No? In other words, I can now measure from 0 to 10 mA. That's why the answer to letter B is 10 mA. Any question with regard to that? Actually, that's how you extend you call it the range of current that a simple analog ammeter. These are analog ammeters, no? A simple analog ammeter can measure. Okay, so this is the same problem that I gave last time. No? Now this time you can solve this using voltage divider and current divider. Last time we solved this. We solved for V last time using KVL, Kirchhoff's voltage law. And we solved for V sub O using Kirchhoff's current law. No? Applying KCL to this particular node. To determine the current flowing through this resistor, if you know the current flowing through this resistor, you can get the output voltage. But this time you can use voltage divider and current divider. So you can determine V here by voltage divider, and you can determine the current flowing through the 10K resistor using current divider. No? So this total current will divide itself between this resistor and this resistor. So once you know the current flowing through this resistor, you can determine V sub O. No? So please just try that on your own. These are the answers which were already given the last time. This time, use voltage division and current division. So that's what I have for today. So here are just some important points to remember. Number one, circuit simplification can be used to simplify the solution of a problem, provided the unknown quantities you are solving for are preserved while simplifying the circuit. Number two, make sure you can properly distinguish when elements are in series and are in parallel. I have seen students make that mistake very, very often. No? Very, very often. They combine two elements that they think are in series which are not in series. Or they use voltage division on two elements which are not in series. Okay, the third point, always check whether a circuit is valid or invalid before you attempt to analyze it. Because if your circuit is invalid in the first place, there is there's no analysis you would be able to do to get a correct result if it is an invalid circuit. Okay, then number 4, you can only use voltage division when the resistors are in series. And number 5, you can only use current division when the resistors are in parallel. So that's it for today. No, again, no, any questions with respect to this material or to